Hello students, we're going to continue our discussion on solutions. We've already talked about what makes a solution. Now we're going to discuss some of the properties of solutions, including concentration and some of the effects of solutes on solvent physical properties. So first we're going to take a look at defining the units of concentration and calculating the concentration of a solute in solution. Here we have a number of different types of concentration measures that we will take a look at. We will mainly focus on percent concentrations and molarity. We can have different percents. We can have mass per mass, which is mass of solute per mass of solution. Volume percent is the volume of the solvent per volume of the entire solution. And then the mass per volume percent, which is the mass of solute for the entire volume of the solution. Notice we have the units. We're usually going to have mass in grams and volume in milliliters. When we're looking at volume percents, we just have to make sure that we're using the same volume unit. So we have to compare liters to liters or milliliters to milliliters. So first we'll take a look at mass percent, and percent concentrations express the amount of solute in 100 units of solution. I like to consider percents like a dollar. So I always think of how can I break down a dollar into the certain number of units that I need. So 10 cents is like 10%. And that's one thing that I use to help me remember or visualize percentages. So when we're taking a look at mass percent, we're going to have the mass of the solute divided by the mass of the solute plus the mass of the solvent. So that means that we have the entire mass of the solution that we're comparing to. How many grams of solute is in the total grams of solution? And we multiply that by 100 to get the mass percent. So this mass percent concentration can be thought of as a conversion factor, where we have grams of solute per grams of solution. So what does that mean? If I have a 90% solution, that means that I have 90 grams of solute in 100 grams of solution. Yes, let me write a note. So let's say, for example, we have a 90% solution. That would be 90 grams of solute per 100 grams of solution, not solvent. And that can be used as a conversion factor. All right, so let's do some practice. What is the mass percent of sodium hydroxide in a solution prepared by dissolving 30.0 grams of sodium hydroxide in 100.0 grams of water? Never mind the little markings on the screen. They will make sense once we go through the discussion. So we know that mass per mass percent is going to be grams of solute divided by the grams of solution times 100. So we first have to start with the mass of the solution, which is 30 grams plus 100 grams to give us 150 grams, which we should really say, to have the right number of sig figs, 150.0 grams. And that's our solution. Now we just divide the 30 by 150 and we get 20%. Notice that we have to have 3 significant figures. All right, let's try the next question. A solution is prepared by mixing 15 grams of sodium carbonate and 235 grams of water. Calculate the mass percent of the solution. So we're given the mass of our solute and the mass of our solvent. We have to add them together. And we end up with 250 grams for our for the mass of our solution. And now we take the 15 grams divided by 250 grams, multiply by 100, and we get 6.00%. Here is a problem where we're going to use mass percent as a conversion factor because we're given the percentage in our problem. Okay, the percentage of gold in jewelry is typically in carats, with 24 carats representing 100% gold. A sample of 18 karat gold would contain 18 grams of gold and 24 grams of metal, which would equal a mass percent of 75%. Calculate the mass of gold in a ring that is 5.5 grams, and it is 18 karat gold. So we know our mass per mass percent is equal to grams of solute over grams solution. And if I want to know the grams of solute, all I have to do is rearrange this equation, and I get the mass percent divided by 100 times the grams of solution. So this is kind of like when you go to the store and you're going shopping and something is on sale for 20%. Well, let's say something is on sale for 75% off. And you want to know what are your savings. So let's say you have something is worth $10 and 75% off. You know that you're only going to pay $2.50 because 75% off is $7.50 off of the original price of $10. Okay, so what we just did was I just multiplied 0.75 times the $10. Okay, so it's the same type of calculation. So what were we given? We've got 24 karat gold is 100%. 18 karat gold is 75%. And that's our mass per mass. And that's 18 grams per 24 grams times 100. All right, but we need to know the amount of grams of gold that's in this ring. That's 5 grams. And it's 18 karat gold, which is 75%. 75.75 times 5.05. Sorry. 0.75 times 5.05 grams equals 3.78, or 3.8 grams of gold. So we know that it's 75%. So what do we have here? The 0.75 is mass percent divided by 100. So 75 divided by 100 is 0.075. And this 0.05 grams is the mass of the solution. So the ring itself is the solid solution, and the total mass is 5.05. All right, so the next type of percent concentration that we're going to look at is volume per volume percent. The exact same calculations as for the mass per mass percent. Notice that we have to have the total volume of the solution. Now, mass per volume, we didn't get there yet. Let me go back. Mass per mass %, what kind of solutions do you think would actually definitely need to use mass per mass percent to demonstrate the percentage? Solids, liquids, or gases? Solid solutions, because why? They're going to be, we're not measuring out liquids, so it would always be the mass of those solids. Whereas if we're looking at a volume per volume percent concentration, we'll be looking at what? A solution involving liquids. Right, so let's say we have two liquids that we're putting together. We end up with the total volume of the solution. Now, mind you that due to intermolecular forces, when you mix two liquids, when their intermolecular forces are very similar, they kind of pack into a nice, let's say a nicer, not packed, but they fit in such a way that they fill up empty spaces between each other. And so, although when we do our calculations for this course, we're just assuming that when we mix two volumes, the volumes are additive. When in actuality, when we mix two liquids, the volume is a little bit less than the actual numerical sum. So let's say we mix 100 milliliters of one liquid, 100 milliliters of another liquid. We're going to use the calculation to say that the total volume is 200. However, in actuality, the volume is actually slightly less than 200. But nonetheless, these are the exact same calculations that we did for mass per mass percent concentration. Now we're just using volume in milliliters. So when you look on a bottle of alcohol, you see a percentage on the bottle of alcohol. Right now, these days, we're looking to make alcohol solutions that can help us fight off different viruses. And the suggestion is that we have 60%. Well, some alcohol concentrations vary. If you take a look, some may be 70%, some may be 90%, some may be 99%. It's just a matter of what you buy. And also, there's actually alcohol in pure extracts that you use for flavorings and seasonings. So let's take an example. A bottle contains 59 milliliters of a lemon extract solution. If the extract contains 49 milliliters of alcohol, what is the volume percent of the alcohol solution? So we know that volume per volume percent is milliliters of solute divided by milliliters of solution times 100. 49 milliliters is the volume of the solute. 59 milliliters is the volume of the solution. And the total, so 59 milliliters is the volume of the solution. So to find the percentage, we take the volume of the solute divided by the volume of the solution, multiplied by 100, and we get 83%. So those extracts that you're using are a high concentration of alcohol. The alcohol actually evaporates off if you're baking them or cooking them. Let's try another. What is the volume percent of bromine in a solution prepared by dissolving 12 milliliters of bromine, of liquid bromine, in the solvent carbon tetrachloride to make 250 milliliters of solution? Why would we use carbon tetrachloride to dissolve liquid bromine? Let's step back for a moment. Why isn't liquid bromine dissolved in water? Why is it dissolved in carbon tetrachloride? Well, remember when we first started our discussion of solutions, remember like has to dissolve like. Liquid bromine, is that a polar or non-polar molecule? It's non-polar. And carbon tetrachloride, is this a polar or non-polar molecule? nonpolar. Although the bonds between the carbons and the chlorines are polar, because this is a tetrahedral molecule, those dipoles cancel out and the whole entire molecule now is nonpolar. So we dissolve a nonpolar substance in a nonpolar solvent. Okay, back to the question. This question is asked, what is the volume percent of bromine if we dissolve 12 milliliters in the solvent to make 250 milliliters? So what is the information that we're given in this question? 250 milliliters is the actual volume of the solution, because it says we make 250 milliliters of solution. 12 milliliters is the volume of our solute. So remember, we divide out the volume of our solute by the volume of the solution times 100, and we get 4.8%. How many milliliters of methyl alcohol are needed to prepare 75 milliliters of a 5.0% solution? This is the same thing once again. When we were looking at the problem with the gold, we need to find out how much is off on that nice dress or pair of pants that we want to buy. So our percent volume is, remember, milliliters of volume, milliliters of solute divided by milliliters of solution times 100. So the milliliters of solute now, when we rearrange, is going to be the percent volume divided by 100 times the total volume of the solution. So it's 0.5%. Oh, I'm sorry, not 0.5%, but 0.05 times 75 milliliters. And we get 3.75, or with 2 sig figs, 3.8 milliliters. Okay. Our 5% divided by 100 is the 0.05, and our milliliters of solution is the 75 milliliters. The last type of percent concentration we're going to take a look at is mass per volume percent. So here's when we're looking at a solid solute dissolved in a liquid solvent. And as always, it's going to be grams of solute over the total volume of the solution. And if we're using a conversion factor, we're going to have grams of solute per 100 milliliters of solution. Always the same types of calculations. We haven't been changing the calculations. The only thing that we've been doing is changing the units that we're taking a look at. So what is the mass per volume percent of sodium hydroxide in a solution prepared by dissolving 12 grams of sodium hydroxide in enough water to make 220 milliliters of solution? So we remember our mass per volume percent is grams of solute over milliliters of solution times 100. So we've got 12 grams divided by 220 milliliters times 100, and we get 5.45, and with the correct number of sig figs, it's 5.5%. Next question. Potassium iodide solution is prepared by dissolving 5.0 grams of potassium iodide in enough water to give a final volume of 250 milliliters. What is the mass volume percent of the solution? Once again, same calculation. 5 grams divided by 250 milliliters times 100, and we get 2.0 grams using the correct number of sig figs. Okie dokie, let's try another. A solution of heparin sodium, an anticoagulant for blood, contains 1.8 grams of heparin sodium dissolved to make a final volume of 15 milliliters of solution. What is the mass volume percent concentration of this solution? Well, what are we given? We're given that we have 1.8 grams of heparin, in 15 milliliters of solution times 100, and we get a 12% solution. How many grams of sodium chloride are needed to prepare 250 milliliters of a 1.5% mass per volume saline solution? Here's when we need to rearrange our equation and get our grams of solute. And that's going to be 0.15 times 250 milliliters, because the 0.15 is 1.5 divided by 100, and we get 3.75 or 3.8 grams. A bunch of our problems ended up with this same numerical value, 3.8. What a coinky dink. Parts per million and parts per billion are also percentages, but they're really, really small units. So if you've ever taken a look at the city water tables, you can find this information out online. You can look it up online, where it tells you the amount of certain trace elements and different substances in our drinking water, and they're generally given in values of, in our drinking water, you can find this for air quality, and those values are given in parts per million or parts per billion. And they're the same percentages, just times 10 to the 6 or times 10 to the 9. So parts per million, that's 10 to the 6 mega, or parts per billion is 10 to the 9. Not tera. Is that tera? Giga. Right? Right. Billion is giga. Tera is 10 to the 12.